Chapter 3.2, Logarithmic Functions. So in this chapter, we'll be introducing the idea of a logarithm, how we can evaluate them, how we can graph them, how they relate to exponents, etc. So, what is the definition of a logarithm? Well, a logarithm with base b of a positive number x satisfies the following definition. For x greater than 0, b greater than 0, and b not equal to 1, we get y equals log base b of x is basically the same thing as saying b to the y equals x. So this is a relationship between the concept of a logarithm and an exponential. These two functions are inverses of each other, so they have this property where you can switch their x and y and solve and all of that, and so the log becomes the inverse of the exponential, as long as the bases are the same. So we read log with the subscript b of x as the logarithm with base b of x, or just log base b of x. The output y is the exponent to which b must be raised to get x. That's how we sort of evaluate a log. Just looking at a logarithm on its own is fairly hard to decipher without turning it into its exponential form, because we know how to figure out most exponentials where we're dealing with a base that is at least an integer value. So 2 to the third is 8. So, but log base 2 of 8 would then be 3. It's a little bit harder to figure that out, though, without just transferring them, and you'll see examples of that soon. Since the logarithm and exponential switch the x and y in inverse fashion, the domain and range of the exponential function are also then interchanged for the logarithmic function. Therefore, the domain of the logarithmic function with base b is 0 to infinity, and the range is negative infinity to infinity, all real numbers. So, recognize that from our previous PowerPoint, we stated that the domain of the exponential, of any plane exponential, is going to be all real numbers. The range is then going to be 0 to infinity. So these sort of just flip-flop each other for the exponential, because, again, that's how inverses work. Now let's do an example. So if you are given log base 6 of the square root of 6, that's equal to 1/2. How would I rewrite that in its equivalent exponential form? Well, I've color-coded it for us, so at least it shouldn't be too difficult to follow through in that way. But essentially, you keep the bases stay the same, so 6, and then the square root of 6 is going to end up on the other side of the equal sign, whereas this 1/2 becomes the exponential, or the exponent, which is something we should know, that the 1/2 exponent is the same as the square root, so we can state that this is, in fact, true. Now, what about taking an exponential and putting it in logarithmic form? Well, again, we're going to keep that base. So the base of the exponential is the same as the base of your log, so log base 3, but these sort of flip-flop the side that they're on. So log base 3 of 9 is equal to 2, like so, written a little bit nicer. But what about when we have a logarithm where we don't necessarily know the output of it? How can we work with that? So again, as I said before, it can be a little bit hard to read log base 3 of 1/27 and just figure out what does that mean. Like, just written that way, I don't necessarily know how to evaluate it. But I would know how to evaluate it in its exponential form. So again, we keep our base the same, and then we're just going to flip-flop our x and y. So 3 to the y power is equal to 1/27. So we take the 1/27th out of the log, we bring the y to the exponent. And now this is something that hopefully we know how to solve. It might take a moment to figure out, but using some exponent rules, what can we do? So, to what exponent must 3 be raised to get 1/27th? So note that we have a number that is less than 1. We have a fraction here. So y will have to be negative. So what must 3 be raised to get 27? That should be an easier question to answer. 3 cubed equals 27. But we're not quite there yet. Because remember, our exponent rule that 3 to the negative third power equals 1/27th. So, y would have to be negative 3. Or in other words, log base 3 of 1/27th equals negative 3. So you're definitely going to need to know your exponent rules to solve problems like this. If you're rusty on those rules, then that's something you're going to want to look into or ask me for help with. Now, we have a couple special types of logarithms that just have slightly different notation. They're special in that they work the same way as other logarithms, but they're the most common logarithms that we use, and so we have quicker ways of writing them essentially. So the common log is the logarithm with base 10. So we write log base 10 of x simply as just log of x. So if you see log of x and no base is written there, assume the base is 10. It's just implied. Because again, log base 10 is used a lot in statistics, etc. So we just wanted a quicker way of writing it, so we just ignore the 10. We get rid of the 10, but it's implied to be there. So if there's no base written there, the base is 10. The common logarithm of a positive number x satisfies the following definition. So again, no, the definition has not changed, it's just that instead of b, we have 10. So y equal to log with no base specified of x is equivalent to 10 to the y equals x. So we can read that as the common log of x, or log base 10 of x, logarithm with base 10 of x, or we can just say log of x, and the assumption is kind of that we're talking about the common log if you don't specify a base. So, for example, if I have y equals log of 1,000, again, this is a log with no base specified, what do we do? Well, there's a couple ways we can go about this. We can turn it into its equivalent exponential form. That's what I would suggest for everyone to do. So that's going to become 10, because again, even though the base is now not specified, we assume base 10 to the power of y is equal to 1,000. And so, again, we're hoping that this is a number that we can sort of figure out, that this is a known answer. And so 10 to what power equals 1,000? You can use your calculator to sort of figure that out if you need to, but hopefully you kind of had an idea. Essentially, there's a trick to it that if you count the number of zeros, you can get your answer. So there are 3 zeros in 1,000, so 10 to the third equals 1,000. I think that's the quick way to figure it out when we're working with nice numbers like that. So common log of 1,000 is equal to 3. The other special type of log we have is called the natural log. So this is a logarithm with base e. So remember, I introduced base e in the previous chapter. It's going to keep coming back. So we write log base e of x simply as ln of x, with no base specified. So once again, log of x, that's log base 10. ln of x, that's log base e. This is called the natural logarithm. Why is it called natural? Essentially, it comes down to the fact that e is very present in nature and stuff, but also it occurs naturally in a lot of weird places. It has a lot of special properties that you might learn if you go on towards calculus. So, once again, y equal to ln of x is equivalent to e to the y equals x. So we read ln of x as either ln, as you can hear me saying, or the natural logarithm, or the logarithm base e, anything like that. But generally, if you say ln, that's fine. It is called the natural logarithm, though. That's ln comes from log natural. I guess it's to keep it consistent that it starts with an L. So, since the function y equal to e and y equal to ln x This should say y equals e to the x and y equals ln x are inverse functions. Ln of e to the x equals x for all x. This is something we're going to address a little bit further, though. A little bit later, though. So just remember that this is an interesting property that we have, but it actually gets a little bit more interesting than that. So here we have that since b to the first power equals b for any base b, so this is something you should know, that 3 to the first power is 3, 7 to the first power is 7, 2.5 to the first power is 2.5. That's how exponents work. So since that's true, we can say that log base b of b is always going to be equal to 1. So that is a basic property of logarithms that you should definitely know. Similarly, since b to the 0 is equal to 1 for any base b, again, greater than 0, not equal to 1, and all of that, so all of our general properties for base b, b to the 0 equals 1. So 1 to the 0 is 1, but 2 to the 0 also 1, 3 to the 0, 7.5 to the 0. Those are all equal to 1. So if we do our property to switch it into its logarithmic form, that means that log base b of 1 is equal to 0. So anytime your base matches the number that's in your logarithm, it simplifies to 1. But anytime it's just a 1 in your logarithm, it simplifies to 0. So this sort of comes back to this property, but again, we will get to that a little bit later when we talk more about logarithmic properties in a later chapter. Okay, so the logarithm versus the exponential graph. So you'll see on the right side here we have all the facts about the exponential function and its graph, the basic exponential y equals b to the x that we learned in the previous chapter. Now let's compare and contrast to how the logarithmic function works. So once again, the logarithmic function is the inverse to the exponential. So what do we know about inverses in general? Well, inverse functions switch their domains and ranges. So our domain and range are the same but flip-flopped, as I said earlier. Now, the graph of the exponential passes through the point 0, 1. So again, remember that when we deal with inverses, we're taking our graphs and swapping over the line y equals x, so that point should also flip-flop our y and our x. So we get the graph passing through point 1, 0, which goes along with that basic property introduced on the previous page. Our function is continuous on all real numbers. The logarithm is also continuous on its whole domain. So remember that its whole domain is just 0 to infinity, but its whole domain. If b is greater than 1, we're increasing the whole time. If b is less than 1, we're decreasing the whole time. Then for logarithms, we get the exact same property. Our graph of the exponential passes the horizontal line test, which it better do, considering that we have its inverse right here. So they both have to pass the horizontal line test. And finally, the exponential graph has a horizontal asymptote at y equals 0. So again, horizontal asymptote right here. So if we're flip-flopping it, if we're reflecting it over the line y equals x, well, that's going to cause a vertical asymptote instead. So our logarithm has a vertical asymptote at x equals 0. Those asymptotes are something you really want to pay attention to when graphing your log, because essentially we're going to be coming back to shifts, and mostly shifts is what you're going to see, but other transformations of logarithms, and knowing where the point, where that special point 1, 0 and where the asymptote is really going to guide you when figuring out what the equation was for the graph, for a logarithmic graph. So here we have a picture. First on the left is log base b of x where b is greater than 1, and on the right is log base b of x where b is less than 1. So I'll remind you that the exponential looks like this instead, or like let's see, more like this. There we go. A little bit ugly, but that's our exponential where b is greater than 1 and b is less than 1. So you can see that there's this line y equals x, and they are perfectly mirrored across it. And perfect is maybe a strong word for how I've drawn it, but they are still mirrors of each other. All right, so here is the graph of three very common logs that we'll see. I guess I shouldn't say common logs since one of them specifically is the common log, but three logs that are used quite often. So we have log base 2 of x, ln of x, and the common log of x. So remember, ln is base e, and e is 2.718, etc. It goes on and on. It's an irrational number. And common log is base 10. So notice that as the exponent gets larger, so from, or not the exponent, but the base gets larger, from 2 to 2.718 to 10, we're actually getting kind of squatter. Like, our whole graph gets kind of shorter, which is interesting, but that's because as our exponent gets larger, or our base of our exponential gets larger, we are getting taller. Like, we move much quicker. So the inverse has to kind of have the opposite happening. Alright, so let's look at how to graph a logarithmic function. So f of x equal to log base b of x is the inverse of g of x equal to b of x, b to the x power. We can see this because their graphs are reflections, as I've shown before. Definitely want to remember this property. So you can see their reflection now actually well drawn. Specifically, remember how these points work. So I've provided this graph here specifically so you can look at these points. So we have 2 to the x and log base 2 to the x. So 2 squared is 4, which means that log base 2 of 4 has to be equal to 2. 2 cubed is 8, so log base 2 of 8 has to be equal to 3. 2 to the 4th is 16, so log base 2 of 16 equals 4, and so on. So these are, so we can go back and forth between these, we're just switching our x and y values. But once again, you always want to track the position of that 1, 0 or that 0, 1 when you're doing a graph of these functions, because that's really going to help you place it in the right place, as well as their asymptotes. Alright, now we get to that inverse property I sort of introduced earlier. So since log base b of x and b to the power of x are inverses for any base b greater than 0 and b not equal to 1, once again, we get that log base b of b to the x. So this is log base b where we are placing b to the x inside of the log, because log is a function, so we have to put parentheses around anything that's inside of it. Sometimes you can fudge that like I did here, but generally you want to put parentheses around what's inside of it just so that you know specifically what is we're taking the log of. So log base b of b to the x, essentially what happens is they cancel each other, so we're left with the x, which means that we get some kind of cool properties from that, which we'll see in the example soon. We also can do the same thing where we start from the exponential. So b to the log base b of x is also equal to x. We know this because that's how inverses work. This is f of g of x, and this is g of f of x. So if you remember back to our chapter on inverses, I believe that was chapter 1.8, this is the definition of the definition of an inverse is if we compose the two functions together and you get x out of it, then you have an inverse. Alright, so let's see that example. 6 to the power of log base 6 of 29. So here, what we're going to do is we're just going to remember this property, that the base of the exponent cancels with that log with the same base. That's how that works. As long as that is the only thing that's there. If there was +2 or something like that, this wouldn't work that way. We'd have to apply some exponent rules beforehand. But because this is the only thing that's in the exponent, they can immediately sort of cancel with each other, and so we will get 29 out of it. Then, similarly, ln of e to the power of x plus 5, notice both of these are in the exponent of e, since there is nothing else in this natural log. If it said natural log of e to the x plus 5 times 2, or plus 7, or anything else, then this wouldn't work. But because it doesn't say that, this does work. We can just cancel, because remember, ln is the natural log, which is base e, so they cancel, and so we just get x plus 5 out of it. So now let's look at the thing that I've sort of hinted at, that you're definitely going to need to know how to do a logarithmic shift. A shift of a logarithmic function or an exponential function. We want to know how to recognize when those functions have been shifted and by how much and how to apply it. So for exponential functions, vertical transformations change the range. But for logarithmic functions, horizontal transformations change the domain. And I know how much we love horizontal transformations. Those are the ones that are always slightly the opposite of what you want them to be. Luckily, we're not talking about stretches and all of that, which are the slightly more difficult part. We're just talking about shifts on this page. So, remember that the reason I say that exponential functions vertical shifts change the range specifically because, well, exponential functions look like this. Their domain is all real numbers, and so shifting them up and down is going to change their range because they have this horizontal asymptote. So it just shifts where their horizontal asymptote is. And so that means that there's nothing below it, which means that their range has changed. Whereas here, with the logarithm, we have this vertical asymptote at y equals 0, and that's the important part. So if I have log base 2 of x plus 3, then that means I've added 3 inside, means I'm going to shift to the left by 3, which means my asymptote also shifts to the left by 3. And so my whole range has now changed. We need to actually, or my whole domain has now changed. To actually state the domain, we need the inside of the log to always be positive. Like, that's the way you can think about it. In the same way that our previous rules. Remember, when I introduced domain, I said there were only 2 real rules you had to think about. Is there division? Is there an even root? Now we have a third rule. Is there a logarithm? So, for division, we can't divide by 0. Even roots, we can't have negatives. Logarithms, we can't have negatives or 0. So that's the difference. It's kind of like figuring out an even root domain, but now we actually have to eliminate the 0 as well. So in this case, I take the x plus 3 and just set it greater than 0 instead of greater than or equal to 0. And I solve. So that's going to be, I subtract the 3 from both sides, so x is greater than negative 3, which is fully reflected right here, because this is negative 3. We can see nothing is on the other side of it. So my domain is x is greater than negative 3. Or from negative 3 to infinity if we state it in interval notation. So in general, the domain of f of x equal to log base b of some expression g of x, some function g of x. So whatever's inside, we just take that inside function and set it greater than 0. So again, if we have log base b of x minus 5, that's our domain is x minus 5 greater than 0. Log base b of x squared plus 3x. That's going to be x squared plus 3x is greater than 0. And you solve and you figure out when this is true, because that's not a full answer, but that's the beginning of you figuring out what your domain would be. So it's just whatever is inside those parentheses is greater than 0. All right. Now let's look at those transformations a little bit more in depth. So for any constants c and d, the function f of x equal to log base b of x plus c plus d shifts vertically by d units up and horizontally by c units to the left. So again, the main thing we're going to see, though, of course, we may see the other types of transformations, particularly reflections, but shifts is the big one. So, when you shift your graph, your logarithmic graph, you want to really pay attention to two things. Where does the vertical asymptote go, and where does that point that 0.01 or 10 go to? So where did this point go, and where did the asymptote go? So if we're doing a horizontal shift, then the asymptote gets moved horizontally, and then that point 10 becomes 1 minus c, 0. So that should be kind of simple to see. But with the vertical shift, it's a little bit trickier because the asymptote stays exactly the same. But our point 10 does in fact change. It just changes in a sort of odd way. So this point 10 is getting shifted up, but we also get this new point that you can pay attention to that is at b to the power of negative d, 0. So that's the new 0 of the function. So we get a new 0, but we also have this point 10 that shifted up. So we get this new point at, that would be 1, d now. So we get several points that you can use to sort of figure out what's going on. So you can use the new 0 to help you figure out what what D and C were, or you can use where 10 moved to. You can also, for sure, pay attention to where that asymptote went. That's a big one. So when we do that shift, we get the x-intercept is at b to the negative d minus c, 0, and the vertical asymptote is x equals negative c. The domain is negative c to infinity, and the range is unchanged. It's all real numbers. Next, we have stretches and compressions. So when we multiply our log by a factor a, we stretch it vertically if a is greater than 1, and compress it vertically if it's less than 1, if the absolute value is less than 1. So we can see that pictured on the graph. Most things remain unchanged in that way. It's very interesting that the domain, the range are unchanged, the vertical asymptote is unchanged, but specifically that x-intercept does not change either, because zeros don't get affected when we multiply by something. Anything times 0 is still 0. Next, we have reflections. So the function negative log base b of x reflects over the x-axis, and so when that occurs, we get the x-intercept unchanged. The vertical asymptote also unchanged, domain unchanged, range unchanged. It's just sort of upside down, but everything else is staying relatively the same. Yes, visually it's different and all the other points have changed, but that special point that we care about hasn't. So you just have to pay attention to what direction you're facing. Then with reflection over the y-axis, we get the x-intercept actually does change now because our x value is being affected. So negative 1, 0, our vertical asymptote unchanged, range unchanged, but our domain has to be on the opposite side now, so now it's negative infinity to 0. Alright, so all of that is to say the properties are not anything new. They're the same things we've dealt with way back in chapter 1.6. We saw them a little bit in the polynomials chapter, where you're going to see this several times. I talked about it in the last chapter with exponentials. Same properties as before, but what's nice about exponentials is that you can track that asymptote, exponentials and logarithms. You can track that asymptote and that 1, 0 that's always going to be there to help you figure out what should be going on. So let's do an example. We want to graph the given function f of x equal to negative 2 log base 3 of x plus 4 plus 5. There's a lot going on here, and I probably wouldn't ask you to do all of this at once, but we're going to do all of it at once. So first, list out our steps. That's what we always start with, is list our steps. Step 1 is we have this horizontal shift left by 4. So shift left 4, then vertical stretch by 2, that 2 in front of the log. Then reflect over the x-axis. And finally, vertical shift up by 5. And let's see how that looks when we apply it to the graph. So we start with our base function, which is in black here, and each of them are color-coded. So horizontal shift left by 4, we can see that the original asymptote here has now shifted over by 4, like that. And then we get the vertical stretch by 2. It really just made it sort of taller, which is how vertical stretches work. We reflected over the x-axis, so now it's upside down. And finally, we shifted up by 5. So that's usually our easy one, so we shift up by 5. And so there's our final function. And where did this special point go? This is our 1, 0, remember? So if I track 1, 0 through our shifts, we get it moved over to -3, 0. Then it stays the same for a couple of, for the vertical stretch and the reflection over x, but our final value is now at -3, +5. So the fact that that point is at -3, +5 can help you figure out how things were shifted. But remember that that +5, that is d, that is this value. But that -3 is one off from this number. So you really want to pay attention to the fact that the asymptote is at -4. That's what's going to tell you what happened there. Alright, so that's it for our introduction to logarithms. We will be talking about logarithmic properties and then solving more complex equations using logarithms in the next chapters. But as always, here's some practice that you can look at before then.